Happy November 3rd. I did this one on Friday. This one I thought was kind of cool actually, so I wanted to talk about it. Like I said, I did it on Friday. Let M be a left R-module and let A and B be Artinian submodules. Okay. Show that the sum of two Artinian submodules is again an Artinian submodule. Okay, so let's see if I can walk through what I did before. It was intuitively clear to me last week. Then you take a break from it and you're like, how did I know it? But then I can't articulate it. Okay, anyway. So we take, if you want, okay, let's just start with the definition of Artinian. Like, if you've never heard that word before, you're like, who the hell is Artin and what's an Artinian? Okay, so like, an Artinian module means that if there is a descending chain of ideals, it eventually stabilizes, as in you cannot keep taking descending chains of ideals. At first, I thought like my mind was going to finitely generated or finite dimension, not finitely generated, I think just finite dimensional modules, and I was like, that doesn't even make sense. There's always going to be a lower bound, right? Because finite. But you can construct modules that aren't finite dimensional by taking countably many infinite products. So, and then you would have to say, okay, well, this module is Artinian if every submodule can be terminated in this specific way. So it's mainly the infinite product case when it comes to constructing these modules that's like the issue. But if you're dealing with like finite dimensional modules, of course you're going to have a smallest one. Like you can't keep taking modules away and not end up eventually with 0 as the lower bound, okay? So if we have two modules that are Artinian and there is a point in where this sequence terminates, like some integer capital N where this sequence terminates for both A and B, let's say A has like A has an integer value capital N and B has an integer value capital N for where the decreasing sequence stabilizes. Okay, we call it terminate, but I mean terminate as in it becomes repetitive, it becomes redundant. So you could say redundancy even. Once this decreasing sequence becomes redundant, we now call it Artinian. For A and B, there is some value M. Now, if we take the sum of A and B, we already know based on just general properties that the sum of two modules is again a module. So if the prelim was like, okay, well, is it even a module first? Okay, well, we know it's a module because modules are additive subspaces. And so if we're taking additive subspaces and we keep adding them, it should stay additive. Like we don't have to worry about closure exploding because A and B will still remain A and B inside of A and B. That can kind of go into like functional analysis type shit, but we won't really talk about that. So let's say now we've already proven or we've already stated, okay, the sum of two modules is again a module. That's been proven. That's a basic undergrad algebra fact, basic functional analysis subspace fact, basic linear algebra subspace fact. So now you have to construct a decreasing sequence of submodules of the module A plus B and show that it stabilizes, aka it's redundant, aka it terminates. So you're looking for an integer, let's say O, such that the sequence now is going to be equal to CO for some O. And beyond that point, you get the same value. You're not going to return anything that's going to cause the sequence to do any other behavior besides constancy. Now, we can define, since this sequence is a descending chain in A and B, you can construct it's almost, I swear, it's almost like a neighborhood basis, okay? It's almost like a neighborhood basis, but we don't want to say it that way, but that's kind of how I'm looking at it. It's like every element now, every element of this sequence, this decreasing sequence of CIs, can be written as A's and B's, because A's and B's are the so-called basis of this module, right? Like every element in the module can be written as like alpha A plus beta B for some alpha beta, and AB and AB. So define AI to be, or A sub I to be C sub I intersects A, that's the first basis element, and then B sub I to be C sub I intersect B, that's the second basis element, okay? So what I said was in an M, but we still have these integers, right? We already know A and B are Artinian, which means they have an integer where the sequence stabilizes. Take AI to be that point where the sequence stabilizes, and then take BI to be the point where that sequence stabilizes for the B's, okay? Now you just have to pick, I call it the worst case estimator. So it may be like, why am I mixing analysis terminology with algebra terminology? Because I don't really see them as different. Like categorically, they're doing the same thing. We're basically looking for a lim soup, right? Like, or a lim imp. A lim imp, sorry. They're kind of the same. That's actually another thing, but like we'll get into that in another video, I think. They're kind of the same freaking thing, the lim soup and the lim imp. It just depends on whether the sequence is increasing or decreasing, but it's basically like a bound for the sequence. So you look for a lower bound for the sequence, that's lim imp, right? The worst case is going to be the maximum. It's going to be the furthest integer out that's going to make the sequence stabilize, and you have to pick the one that's going to capture it for B and that's going to capture it for A, okay? Because if you picked, let's say that N sub B is at the 10th spot and N sub A is at the 11th spot, right? If you cut it off at the 10th spot, you haven't captured where A stops at the 11th spot. So you have to pick the bigger one. So pick the max of these two values. Since every sequence CI, every decreasing sequence indexed on the CI can be written as a combination, and when we say combination, we're talking about this sum and this intersection, can be written as a combination of these A's and B's. It must be the case, right, that the CI, this subsequence that's inside of this AB module, this AB Artinian module, is going to stabilize whenever A stabilizes or whenever B stabilizes, whichever one stabilizes second. It stabilizes when the later one stabilizes. It has to, because it was written in terms of that one. And if it's using elements from that Artinian module already, then it's forced to stabilize when that module stabilizes, okay? So that's part A. So that's why the sum of two Artinian modules is again an Artinian module. Okay, now as an exercise, or maybe as like a little thought, is it true then that the sum of two Noetherian modules is again a Noetherian module? And why or why not? Like, think about it. And you can use this same argument. So a Noetherian module is one where you have an increasing sequence of submodules and it terminates. So you can't infinitely add modules, whereas Artinian is infinitely taking them away. You can infinitely take away submodules if you have an infinite generation of submodules, obviously, right? That's why I was saying like finite dimensional modules in my head. I was always thinking of finite ones. I was like, what the hell is Artinian even doing if we're in finite dimensions? But that's not always the case. It's just that you don't see those modules constructed usually because it does lend itself towards analysis to even think about it. Because when you get into infinite sequences and series, okay, now you're thinking about analytics. But it happens. So now here's the interesting part, maybe. So if R is also a left Noetherian and M is finitely generated, show that M has a unique maximal Artinian submodule and that A of M mod AM is equal to 0. Okay, so like this may seem like a lot, but I'm telling you, it's like intuitive once you get it. Once you get it, it makes sense, right? That's like the whole thing. Okay, so here are some notes that I wrote in blue because at the top of my head, I was like, okay, wait, what is this even saying? So, finite generation is about spanning size and not chain finiteness. Now, this little blurb that I wrote right here is probably the key to like me kind of distinguishing between finitely generated and the Artinian and Noetherian properties, because finitely generated does not mean that there are like finitely many modules, submodules, like stuff you can finitely generate something and then combinatorially take it to infinity. So it can be generated by a finite amount of things, but like a free product essentially. I think that's like the best example. So okay, here's some like more concrete examples. So infinite direct sum copies of a field K is not Noetherian or Artinian. Like literally look at it. Because look at what's happening. Like again, it looks like a free product. Like you're basically just like exploding all of the possible K's that you can. There's no way you're going to decrease it to 0. There's no way you can stop increasing. It just keeps going. It almost looks exponential. And then, okay. And then number 2, it says the infinite product is Artinian / Noetherian as a module over itself only if the ring is semi-simple. Okay, I don't really want to get into this one. I don't really want to get into that one. For K is a field, it works. I don't want to talk about semi-simple rings. We'll get there. I don't want to throw too much in here. We'll get there. Okay, so property. A Noetherian ring has infinite ascent. If it's Noetherian, it means that you cannot add infinite submodules. Like you won't explode. Okay? Infinite addition of new submodules. That's where it violates. Artinian means peeling off infinitely many components. These are the violations of it. When I'm not writing the definition, I just want to say this violates. This violates Noetherian. And then this violates Artinian. Okay. And then finitely generated infinite breadth, which means requiring infinitely many generators to span the space. This violates finitely generated. Okay. Note, if both submodule constraints hold and the base ring is Noetherian, then the module is finitely generated. Why? Modules themselves are rings acting on things. If the ring is not sufficiently controlled, its actions will explode the space. So now let's look at the solution, okay? And this is what I wrote before I decided to clean it up with ChatGPT. And this elliptic curves is for something else. Hold on. I said review elliptic curves. Don't even... We're not doing algebraic geometry yet. We will. Okay, so... Solution. M is finitely generated. Show M has a unique maximal Artinian submodule AM in that any other Artinian submodule that's remaining has to be the trivial submodule. Now, do you see the way that I read this? If you read it out loud and you understand what the symbology is representing, it's actually clear that these are equivalent statements. Okay, show M has a unique maximal Artinian submodule AM and any other Artinian submodule remaining is the trivial submodule. Now think about it. If AM is the unique maximal Artinian submodule, it's unique and it's maximal, then if we took the whole space M and we removed the unique maximal Artinian submodule, there should be no other submodule that's maximal. And if you took away the, and if, right, that's it. Because this, okay, look, there should be no other submodule that's maximal. That's exactly it. Okay, so define the candidate. Okay, so from part A, we know that the sum of two Artinian R-submodules is again another Artinian R-submodule, right? And you can take that by induction. If two of them make another Artinian submodule, then take the collection of all of them and sum them up. That itself is another Artinian submodule by the proof we just did. Okay, so here's our candidate. Now, the issue now is like, how do we know it stabilizes? Because we can keep taking infinite sums and we can keep growing this submodule. Okay, so how do we know it stops? We know it stops now because we were given M is finitely generated and R is left Noetherian. Okay? And so because of that, the Noetherian condition assures that the sequence stabilizes, and thus there is a maximal Artinian submodule uniquely. Because now we have the Noetherian condition, which says that this increasing sequence, right, has to stop. If you violate Noetherian, that means that you can have an infinite addition of new submodules, right? Which is what this was going to be. This would have been an infinite addition of new Artinian submodules, but that can't happen because the ring underneath is Noetherian. It's going to stop it from blowing up. Exploding the space is what I say. Now, now here I said the statement is equivalent. That's just me being lazy. I was like looking at a talk at the time and I just wrote that down because I didn't feel like proving it. So we have the unique maximal one, right? So now to show that if we take M, which is finitely generated, by the way, and this is the unique maximal Artinian module, then any other Artinian module of M, any other Artinian submodule of M has to be trivial. Okay, suppose for contradiction that there exists a non-zero, right, Artinian submodule such that when we take n mod a sub m, it's contained in m mod a sub n. Now think. Suppose there's another one where this happens, right? Okay. Then its pre-image would be an Artinian submodule containing a sub m strictly. This contradicts a sub m being maximal. Hence, no n exists. That's like that's why I mean by it looks like it's an equivalent statement. Once the maximal Artinian submodule is formed as the sum of all Artinian submodules, the quotient contains no Artinian part remaining. That's the key part. Is this a sub m was defined to be all Artinian submodules, and we know this sequence stops, which means we've contained all Artinian submodules. So there is no other Artinian submodule, which means the second part of the question has to be fulfilled because we constructed the unique maximal Artinian submodule that contains every other Artinian submodule in the space. So then if we took M and we quotiented it out by all of the possible Artinian submodules, the only thing that's going to be left is trivial. And that's the proof. Bing, bing.